So the second approach here is going to be like significantly more modern, I guess is the adjective a lot of people would use. It's going to follow this more algebraic approach of Dedekind. Rather than focusing on the properties of symmetric polynomials, it's going to focus more on the properties of integral extensions of rings. So the basic idea is to try to generalize the proof that basically the proof of the analogous result in the field setting. So the idea is to generalize the following proof. Okay, I'm not going to... So I guess first we need to know what we're proving, right? So the fact that if E contained in F, let's say this is an extension of fields, then the elements of F algebraic over E form a ring. So here, I guess, notice that really all we're changing in this setting is, E is no longer an integral domain, it's a field. And I'm changing the word algebraic to integral. Okay. I guess maybe I should remind you the actual result that I'm going to prove today. So aside. I guess maybe aside isn't the right word. We give another proof that if A is an integral domain, and let's say L is a field containing A, then the elements of A, the elements of L integral over A, meaning that they satisfy a monic polynomial with coefficients in A, form a ring. Okay, so this is the ultimate goal, and essentially the new proof that we're going to give follows the structure of the proof of this fact here. So the proof of this fact, really, there are two useful, like two sub-facts that make up this big fact. Okay, to prove this we need, so an element alpha and F is algebraic over E if and only if E adjoin alpha. So the smallest subfield of F containing E and alpha is a finite extension of E, meaning that it's finite dimensional as a vector space over E. 2. The second second useful fact about this is that, finite extensions are transitive. I guess the condition of being a finite extension is transitive. What do I mean by this? I.e., if, let's say, E is contained in L is contained in F, and, well, maybe E and F I shouldn't use. Let's just say I have fields. Let's say L contained in M, contained in K, and M over L and K over M are finite. And so is the big extension K over L. So essentially, if this is finite, I'll just write less than infinity, and this extension is finite, then the whole thing is finite. Okay. So these two conditions together, basically, if I know fact 1 and fact 2, then this statement is pretty easy to prove. So given 1 and 2, I'll call this underlined thing star. Given 1 and 2, star follows easily. Basically, if alpha and beta and F are algebraic, then what do I want to say here? Then using 1 and 2, so by 1 and 2, I guess, yeah, by 1 and 2, E join alpha beta is a finite extension. This is E join alpha join beta is finite over E, and thus so are E adjoin alpha plus beta, which is contained in this thing, and E adjoin alpha times beta, which is contained in this thing. Okay. So alpha plus beta and alpha times beta are algebraic. Over E by 1 and the result holds. Okay. So since the sum of two algebraic numbers are algebraic, the sum of two elements of F algebraic over E are algebraic over E, and the product of two elements of F algebraic over E are also algebraic over E. The elements of F algebraic over E form a ring. Okay. And so the idea for our proof of this statement here, that the elements integral over an integral domain form a ring, we're going to try to basically replicate these two facts. It's going to be a little bit more work, but once we have the analogs of these two facts, then we'll be able to prove the result. So The goal, so goal for the rest of the lecture is to come up with analogs of 1 and 2 and prove integral elements form a ring. I should mention here that there are like certain properties of field extensions that I used here without really mentioning them, and we'll have to worry about them a little bit more. The proof again won't be quite as simple in the integral case as opposed to the algebraic case. Like for example, here I use the fact that sub-extensions of finite extensions are still finite because subspaces of vector spaces. Yeah, because yeah, subspaces of vector spaces are finite dimensional and stuff. Okay, yeah. So there'll be a bit more to worry about. Is I guess the moral. First, we're going to come up with an analog of this condition 1, which is essentially a criterion. So what is condition 1 here? It converts the question of being algebraic into a question about this extension E adjoint alpha. So the analogous thing for integral extensions is as follows. Let A be an integral domain and L a field containing A. Then how do I tell if alpha and L is integral? Integral over A if and only if. Okay, so again, I look at what happens if I look at A adjoint alpha. This time, rather than the field generated, I'm going to look at just the ring generated by alpha. If and only if A adjoint alpha I guess maybe I'll state this more carefully, and then I'll see that A adjoint alpha is the thing that I'm really interested in. So if and only if there exists a non-zero finitely generated A submodule of L I'm going to call this M such that alpha M is contained in M. Okay. So essentially what you should think of as okay, I've got basically this is what I think of when I think of this result. I've got some field L, so I'm thinking maybe of L as like C or something like this. So maybe a plane, and I'm thinking of A as Z, for example. This is probably the simplest possible case. And a Z submodule of C is basically a lattice in C. So it's kind of like this constellation of points. So if I can find, so if I've got this, so in this example, complex number that takes my lattice inside my lattice, so like when I multiply the whole, when I rotate and scale my lattice by alpha, I still end up in the lattice, then that element alpha had to actually be integral over z. Okay, this is kind of like the way I'm interpreting this. This is how I think about this heuristically. Is if I can find a lattice in C that transforms nicely with respect to alpha, then alpha actually has to be integral. Okay. So how do we actually prove this? I guess before I prove this, let me just give you the corollary and the way we'll apply this. Corollary. So I'm going to let A and L be as above. Okay. An element alpha in L is integral if and only if A join alpha is a finitely generated A module. So I guess there are a couple questions that arise. So first of all, to see how you prove the corollary from the proposition, one direction is very easy. If alpha in L is integral, then A join alpha is a finitely generated A module. You can check this just using the definition, and we'll see, like in the proposition, I'll basically prove this part, or I guess that's how you prove the part in the proposition. Yeah. So in the proof of the proposition, I'll prove the if part of this, or the only if. Sorry. Yeah, I'll prove the only if part when I prove the proposition. The if part, so if A join alpha is a finitely generated A module, well, to prove that I use this proposition here. That's why this is a corollary. If this is a finitely generated A module, clearly alpha times this thing is contained in itself. And so A join alpha satisfies the conditions of this module M. So the corollary says, like, instead of having to worry about finding an M, all I really have to do is check for this one, A join alpha. Just check if this is finitely generated. Okay. The advantage of having this proposition basically says that basically it happens sometimes where checking that A join alpha is finitely generated is harder than finding such an M. Okay, and we'll use this version, this statement of the proposition, ultimately in our proof of the fact that integral elements form a ring. Okay. So first, let's prove the proposition. Proof proposition. Okay. So the first direction is easy. If alpha in L is integral over A, I can find some polynomial, some monic polynomial with coefficients in A that it satisfies. Assume, let's say, alpha to the n plus A sub n minus 1 alpha to the n minus 1 plus dot 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 plus A naught. Let's say this equals 0. Then m equals A join alpha is generated by 1 alpha to the n minus 1, okay, over A. So this check is fairly easy to do. Okay. The next condition, or the other direction is a little bit more work. So suppose I have such an M. So now we prove the converse. Suppose M is contained in L, a finitely generated A module, and alpha times M is contained in M. Okay. So the key result is some kind of seldom used result from linear algebra known as Cramer's rule. Okay, so we use something called Cramer's rule to construct a polynomial with alpha as a root. So first, let me go ahead and state Cramer's rule. So I'm going to let, let's say, Cij, these are going to be elements of field L with 1 less than or equal to I, j less than or equal to M. And suppose for each I, 1 less than or equal to I less than or equal to M, I know the following. I know that the value of the sum from j equals 1 to m, Cij times some xi is equal to some number di. Okay. Then I can recover these xi's, xj, sorry, these xj's are the determinant of some matrix Cj divided by the determinant of the matrix C, where, okay, what is this matrix C and what is the matrix Cj? Well, C is the matrix with entries Cij. Okay. And Cj is essentially, you take the matrix C, but you replace the jth column. So you replace the jth column, instead of having, Cij's throughout, you're going to have these d sub j's. Or, yeah, d sub I. Than c sub ij. Okay, so, what does this tell me? It essentially tells me how to get the solutions to a system of linear equations out of some matrix. Now, you do have to be a little bit careful here. I guess this is provided. There's a little asterisk here. Provided, that C not equal to 0. Okay. If you multiply this det C to the other side, then everything's still fine. This equation works regardless of whether det C is 0 or not. Okay, so to prove this essentially, so just a remark on the proof. To prove this, expand the determinant of Cj, which will look like C11, Cm1, C1j, xj. Sum Cmj, xj. So essentially, expand this out using some cofactors. The tedious way to compute a determinant, and compare this to det C multiplied by x sub j, and you'll be in luck. Okay, so we want to essentially use Cramer's rule in this proof. We're going to need to come up with whatever this matrix C is and whatever these d sub ij's are. Okay, that's essentially, to use Cramer's rule, I need to come up with what my matrix C is and what these elements d sub I are. Okay. So let's say I have generators for M. Let M be generated by, let's say, V1 through Vn over A. So I know by assumption M is finitely generated. Okay. Since alpha M is contained in M, we can write alpha times V sub I. Well, this has got to be some A linear combination of the other V sub j's. So I'm going to call this Aij V sub j. Okay, and these Aij's are going to play the role of myCij's. Okay. Now, rearranging these equations, sorry, that's not entirely true. They're going to be very closely tied to myCij's. So rearranging this equation, so just subtracting everything over, is going to give me negative AI1 V1 minus, so it'll be a bunch of negative signs, minus AI Sorry, one second. I'm a little worried about my indexing here. Yeah, okay, the I will be constant throughout. Sorry, yeah. The I is not going to change. The J is going to change. Okay, so it'll be AI I minus 1, V sub I minus 1, and then on V sub I I'm going to have a different coefficient. I'm going to have minus, or I'll have plus alpha minus A sub I times V sub I minus, and so on. Okay. AI I plus 1, V sub I plus 1, minus, you know, AI and Vn. Okay. And this whole thing is going to be equal to 0. So these are going to be my D sub i's, and these are going to be my C sub ij's. Okay. So they'll almost always be negative aij, except for CII will be alpha minus AII. Okay. So we then apply Cramer's rule. With di equals 0 always, xi equals vi, and cij is going to be negative aij if I is not equal to j, and cii is going to be alpha minus aii. Okay. So what does Cramer's rule tell me? It tells me that Cramer's rule since notice that C sub j so has a column of zeros. Right, so if I replace the jth column with all these D sub i's, which are all 0, I'm going to have a column of zeros. That's going to have determinant 0. Determinant of C sub j is going to equal 0. So using our possibly non-invertible version of Cramer's rule, I'm going to get that the determinant of C times x sub j is equal to 0. This determinant of C times x sub j is equal to 0. Okay, so I guess really x sub j should really be v sub j. And maybe I should have assumed this at the beginning. We can assume without loss of generality that these v sub i's are all non-zero. Choose non-zero generators for m. Therefore, since we're working in a field, this determinant actually has to be 0. Thus, determinant of C equals 0. If you expand out this determinant, what will you find? Okay, so if you actually like write down what this expansion is, so the entries are either I sub or A sub ij's, which are elements of A, or I guess, sorry, I should have marked that here. So since these generated M over A, we can assume these aij's are elements of A. So the elements of this matrix C are either A sub ij's, which are elements of A, or they're this alpha. So this determinant is going to end up being, we see it is actually a monic polynomial. Monic polynomial with entries in A. Or not, sorry, not entries. I should say coefficients. Okay. And what do we notice? What do I want to say here? I think this whole sentence actually doesn't kind of make sense. Expanding this determinant out, I should really say we see it. We see, I should say, it is a monic polynomial with coefficients in A evaluated at alpha. Okay, that makes sense now. Since when we evaluate this monic polynomial at alpha, we get 0. Thus, alpha is integral over A. Okay. So this is the proof of this first result. It is an analog of 1. It says basically it says that an element is integral over an integral domain if and only if when I join that element I get a finitely generated module over the integral domain. And okay, I think this is where I'll stop for this video. In the next video we'll prove condition 2, and if it doesn't take too long, we'll combine 1 and 2 to prove the result.